A quiet American street looks ordinary from above, but beneath its asphalt begins a hidden planetary story. Every passing tire moves across a surface thinner than most of us ever imagined beneath our daily lives. Below the pavement, the familiar world gives way to stacked layers of soil, rock, and ancient pressure. If Earth was scaled to a city block, our surface would be only the thinnest painted line. The descent leaves basements, roots, and pipes behind, entering ancient rock that no streetlight ever reaches. But Earth is not a hollow sphere waiting below us. It is layered, dense, and alive with heat. The farther we travel inward, the more ordinary ideas about solid ground begin to fail around us. Deep signals, not cameras, are the clue scientists use to imagine this hidden interior of Earth. At the center waits a metallic world, inferred from evidence, but never seen directly by human eyes. This journey begins with one question. What does that unseen engine do to the surface above? The glow below is not fantasy footage. It is a careful model built from planetary clues. From this hidden center, the investigation rises again toward compasses, satellites, auroras, and the sky above us. A compass needle seems simple, yet its motion begins with forces far below the road beneath it. The needle turns because Earth itself behaves like a planet-sized magnet with a restless, hidden source. That source is not in the air above us, but deep inside Earth's moving metal layer. For centuries, navigation depended on a field most travelers could feel only through a small needle. Today, satellites and power systems still live inside the wide reach of Earth's magnetic environment every day. The core does not touch these machines, yet its influence stretches far beyond the ground itself. Above the atmosphere, invisible magnetic lines form a vast shape carved by the solar wind around Earth. This shield is not a wall, but a changing region where charged particles are redirected through space. When those particles stream from the sun, Earth's magnetic field bends their path around us in space. Some particles still enter near the poles, turning the upper atmosphere into glowing, moving curtains overhead. The aurora is beautiful, but it is also a visible clue to invisible planetary forces below. A glow over Alaska can trace back to motion thousands of miles beneath your feet tonight. The strange link between sky and core is one reason this hidden world deeply matters today. Without a global magnetic field, Earth would face space weather in a very different way every day. Scientists do not describe the magnetosphere as perfect protection, but as an important planetary buffer around Earth. That distinction matters because the field changes, bends, weakens, and strengthens across long spans of time. To understand those changes, we have to follow the signal back toward its buried source again. The trail leads away from satellites and auroras, down into a rotating ocean of metal below. This metal moves slowly by human standards, but powerfully on the scale of a planet below. Heat escaping from deeper layers helps drive circulation through the liquid outer core below us today. As the planet rotates, those currents organize into patterns that can generate a magnetic field below. The process is called a dynamo, though Earth's version is larger than any machine humans build. A dynamo turns motion, an electrical conductivity, into a magnetic field that surrounds the entire planet. The idea sounds mechanical, but the reality is turbulent, ancient, and still partly mysterious inside Earth. No probe has reached the outer core, so every image must remain a scientific visualization today. Still, the evidence points to deep, constantly renewing Earth's magnetic field across human lifetimes and centuries. The field reaches through rock, ocean, air, and the dark space surrounding our planet every day. A backyard compass and a polar aurora are connected by the same hidden planetary system below. That connection turns the core from a remote object into part of everyday Earth itself today. But the next question is harder. How do we know any of this is true today? The answer begins not with drilling, but with earthquakes moving through the planet after sudden ruptures. Each tremor sends waves through Earth, and those waves change when they meet hidden layers below. The planet answers in vibrations, giving scientists a way to listen below the surface without descending. An earthquake begins rupture, but its aftermath becomes a message traveling through stone far away across distant monitoring stations. That message arrives at different times, shapes, and strengths after earthquakes far away. Sensitive instruments record movements too small for the human body to notice during an ordinary day. One local tremor can become a global map of hidden paths through Earth's interior layers below. As the wave approaches the core boundary, the hidden engine becomes a question again in darkness. The first clue is almost nothing, a trembling needle, turning one distant earthquake into a readable trace. No scientist sees the core directly. They study signals that arrive after crossing the planet's interior. Seismic waves spread outward, bending through Earth like ripples crossing a body hidden beneath every continent. A jagged line on paper becomes evidence because deep motion leaves patterns that instruments can remember. Some waves speed up, slow down, bend, or fade, depending on what kind of material they cross. Where the waves grow silent, the planet begins asking a stranger question about its hidden center. A quiet fault line can become a planet size scanner when stored energy suddenly tears through rock. One earthquake sends clues through the mantle, around the core, and back toward instruments waiting at the surface. The path downward is not opened by drills, but by careful listening from thousands of miles away. The next clue is not a photograph, but a pattern the planet cannot hide from measurement. The seismic wave dives deeper, curving as pressure and density change beneath landscapes we think we know. By comparing arrival times, scientists begin sketching boundaries that no camera has ever directly crossed inside Earth. A delayed signal can point toward a hidden layer thousands of miles below the quiet recording room. It is like reading a basement pipe by listening carefully from across an entire city block. Why do some waves pass through deep Earth, while others seem to disappear inside the planet? Shear waves cannot travel through liquid, so their absence becomes a powerful clue about the outer core. The missing signal is not a failure in the instruments. It is evidence of liquid metal below. In a comm room, researchers reconstruct violence that began far beneath another continent and traveled through stone. Each path adds a constraint, narrowing what Earth's unseen interior could realistically beneath the surface. The map remains unfinished, yet one deep boundary keeps appearing in almost the same place worldwide. That boundary marks where solid mantle gives way to a stranger metallic region deep below us. Rock textures fade into denser possibilities, where pressure compresses matter beyond anything familiar at the surface. Earth's mass tells scientists the interior must hold something denser than ordinary crustal rock near us. If Earth were scaled to a city block, the crust would be thinner than an outer skin. Gravity measurements add another clue, revealing how hidden mass is distributed. unevenly beneath the planet's surface. What hidden material could explain the waves, the weight, and the magnetic behavior together beneath Earth? The core is inferred from many clues agreeing, not from one dramatic discovery beneath our feet. The model grows stronger when Earth records, gravity data, and magnetism begin pointing toward the same structure. When the numbers disagree, scientists revise the model until Earth's behavior becomes more coherent as a whole. Those clues now lead downward, toward the deep place where Earth's magnetic story begins, inside metal. Under a dark sky, a compass needle, an aurora hint at forces rising from deep Earth. The needle turns because Earth itself behaves like a vast magnetic system, surrounding every surface journey. A process thousands of miles below can connect to charged particles far above the atmosphere overhead. Moving conductive metal can generate electrical currents, helping sustain a magnetic field around the planet itself. But if the core is hidden, how do scientists know the magnetic field changes over time? Historical measurements show magnetic north does not stay fixed like a painted mark on a map. The field is not a rigid shell. It moves, weakens, strengthens, and reshapes slowly across centuries. Traffic patterns on a highway, changing flow inside the core can shift the whole system. To understand the moving field, we have to approach the moving metal that may drive it. The evidence now points from surface instruments toward the liquid world. Those instruments imply deep below. At the outer core's edge, the familiar language of rock begins giving way to metal below. Tiny mineral textures suggest a boundary where heat, chemistry, and pressure change together deep below Earth. The core mantle boundary is not a doorway to visit, but a transition scientists can detect indirectly. A signal recorded at the surface may carry a story from this unreachable depth back upward. The invisible core becomes believable because independent clues keep pointing toward the same internal structure again. What scientists build is not a fantasy world, but the best map the evidence allows today. If we could descend past the clues, what would the journey actually feel like inside Earth? The next chapter leaves instruments behind and follows the layers themselves downward through imagined descent, one by one. The path begins under ordinary ground, where solid rock hides the first stage of descent below. The descent starts in the crust, a thin outer shell compared with the planet below it. The descent begins where Earth shows its age plainly, in canyon walls layered like a broken history book. Each band of stone records pressure, weather and time before the story drops beyond human reach. A borehole light enters the crack, but even our deepest tools barely scratch the planet's outer skin. If Earth were a city block, the crust we know would be thinner than a painted line. Below that thin, familiar shell, the rocks become hotter, heavier, and far less like the surface. The camera follows a fracture downward, turning ordinary stone into the entrance of a hidden planetary system. At first, depth looks like darkness, but the real change is pressure squeezing every mineral tighter. The deeper path is not a tunnel humans can enter, only a model built from signals. Those signals begin with earthquakes, passing through Earth like sound through a massive, sealed planetary instrument. What they reveal is unsettling. The world beneath us is layered, active, and never completely still. The mantle begins below the crust, not as open lava, but as solid rock under impossible heat. Over human time, it seems motionless. Over geological time, this rock can slowly bend and flow. That slow movement matters, because even solid materials change behavior when heat and pressure keep rising. The scene stretches like warm tar, a comparison that helps without turning the mantle into liquid. Here, science asks us to hold two ideas to their solid rock can still move over time. Mineral grains press against each other, deforming so slowly that a lifetime would miss the motion. A glowing model follows the stress, showing flow patterns without pretending a camera truly filmed them. From this depth, the surface feels impossibly delicate, like a roof over a restless stone ocean. But the mantle is not an ocean of fire, it is a slow engine of rock. Its movement helps recycle Earth's surface, linking deep pressure to continents, trenches and volcanic chains above. As the descent continues seismic, waves become the only lanterns guiding scientists through the hidden dark. Some waves pass through deep material, while others bend slow or disappear at hidden internal boundaries. Those changes let researchers map layers that no drill camera or deep submersible could ever reach. The path grows denser, and every signal carries a clue about temperature, composition, depth, and pressure. Pressure now dominates the story, forcing atoms into arrangements that would be impossible near the surface. A football field of rock above becomes a crushing column, multiplied thousands of miles downward into darkness. Yet even under that weight, Earth is not simple. Boundaries ripple, thicken, and change unevenly below. The lower mantle appears less like a flat layer and more like a complicated, deep landscape. Seismic shadows suggest that something major waits ahead, where dense rock finally gives way to metal. Before the core appears, Earth offers one more puzzle, a boundary scientists can only infer indirectly. The core mantle boundary is not a painted line, but a rough transition under extreme, hidden conditions. Here, ancient slabs may sink toward hotter regions, changing how heat escapes from the deep planet. The visual becomes stranger, because the science does too, is measured carefully, not visited. Seismic waves skim the boundary, returning distorted clues from a surface thousands of miles below us. Some regions may be hotter, denser, or chemically different, creating patches in the hidden lower terrain. The boundary behaves like a planetary frontier, where slow rock approaches a very different metallic world. A faint shimmer appears in the model, hinting that the next layer will not be rock. The viewer is still above the core, but the evidence now points toward moving metallic material. Every clue from this depth arrives indirectly, filtered through mathematics, instruments, scientific modeling, and careful uncertainty. That uncertainty does not weaken the story. It shows how science maps places we cannot enter. At last, the descent reaches the edge of the outer core, where rock meets liquid metal. The color shifts from mineral glow to a heavier metallic radiance, dense, pressurized, and almost alien. Unlike the mantle, this layer can flow as an electrically conducting fluid under crushing deep pressure. It should not look like lava. It is stranger, deeper, denser, and more metallic than fire. Tiny simulated particles trace movement, revealing currents that may power Earth's magnetic behavior far above. The hidden engine is beginning to appear, not as a machine, but as motion inside metal. Rotation, heat and composition work together here, turning depth into a planet-scale electrical system below us. The camera holds on the boundary, where the familiar story of rock finally ends in shadow. Beyond this edge, Earth's deepest ocean is not water, but pressurized metal already in motion. And once that metal begins to move, The next question becomes unavoidable. Can it shape the sky? The descent reaches a boundary where solid rock behavior gives way to something stranger and far less familiar. Here, the planet stops feeling like stone and begins to behave like a machine under pressure. The last rocky layer fades behind us, while a deeper metallic glow begins to fill the darkness. At the outer core, Earth hides an ocean that is not water, but moving liquid metal. This world is buried so that no drill camera or human machine can approach it. Yet seismic waves suggest this layer flows bends and carries energy around the planet's center. The metal is mostly iron and nickel, heating far beyond anything found on Earth's familiar surface. But heat alone does not explain the motion. Pressure, rotation, and cooling all shape the flow. Imagine a foundry stretched around the planet, except every current is trapped under crushing gravity and darkness. The camera follows a slow metallic current, glowing through darkness like weather inside the deep earth. These currents do not move like rivers we know, because the entire planet is rotating around them. Rotation twists the flow, organizing motion that would otherwise be chaotic, like storms on a hidden radar. Small differences in temperature can begin large movements when the surrounding metal is this deep and dense. Hotter material rises slowly from below, while cooler metal sinks, creating circulation through the outer core. This circulation is called convection, and it is one of the engine's most important moving parts. Nothing here has a calm surface, only pressure, heat, and metal constantly exchanging enormous amounts of energy. The outer core may be invisible, but its movement leaves magnetic fingerprints that reach the surface. A compass needle on a quiet road responds to forces born thousands of miles beneath it. That connection feels impossible until the outer core is seen as an electrical conductor in motion. Moving conductive metal can generate electric currents, and those currents help build a planet-wide magnetic field. This is the basic idea behind Earth's dynamo, though the real system is far more complex. The dynamo is not a single spinning wheel, but a restless pattern of motion and feedback. As metal moves, magnetic fields form. Those fields can then influence how the metal keeps moving. The result is a self-sustaining process, powered by heat escaping from the planet's deep interior. But the engine is not perfectly smooth, and that imperfection may explain why the field changes. Some currents strengthen the magnetic field, while others may weaken, twist, or redirect it over time. This is why Earth's magnetic field has never been a perfectly still or symmetrical shell. It drifts, pulses, and records the deep, metallic motion that humans can never directly watch from above. The outer core also helps scientists understand why Earth is different from many rocky worlds nearby. A planet can have rock mountains, an atmosphere, yet still lack a strong global magnetic field. Earth's hidden ocean of metal may be one reason our sky behaves differently from Mars. That comparison matters, because planetary interiors can shape conditions far above their visible surfaces and atmospheres. The camera pulls outward from metallic turbulence to a faint outline of Earth wrapped in field lines. For a moment, the deepest layer and the highest atmosphere seem connected by one invisible system. This connection is not magic. It is physics operating across scales the human mind struggles to hold. At this depth, one slow motion can matter more than 1,000 storms on the surface. But scientists still debate details of the flow because the core must be studied from indirect signals. Every earthquake becomes a kind of probe, sending waves through places no instrument can physically enter. Some waves slow, bend, or disappear, revealing crucial clues about liquid metal beneath the mantle boundary. Those clues do not show a picture. They build a scientific model, tested again and again. The best models suggest a dynamic outer core, constantly shaped by heat loss and planetary rotation. Still, every model carries uncertainty, because the real core remains locked far beyond human reach today. That uncertainty makes the outer core less like a solved fact and more like an ongoing investigation. The deeper the camera travels, the more the metallic flow looks both violent and strangely controlled. It is chaotic in detail, yet organized to influence the entire planet above our heads. A city block, a forest, and an ocean all sit above this hidden metallic motion below. Without seeing it directly, we still live inside the consequences of what this hidden engine does. The next question is how this moving metal sends its influence far beyond the rocky Earth. To answer that, the Geology must follow invisible magnetic lines rising from the core into space. The shot ends as metallic currents fade into glowing field lines, pulling the story upward towards space. At the edge of space, a faint boundary hints that Earth's hidden engine reaches far beyond the surface. The sun constantly charged particles outward, pushing invisible pressure toward Earth like a restless cosmic wind. Earth's magnetic field is not a wall, but a guiding pattern that changes how particles move. A motion thousands of miles below can shape a region stretching far past the planet itself. Satellites watch this invisible environment from above, translating magnetic changes into signals that scientists can compare and measure. Because no one can visit the core, every distant measurement becomes another clue in the investigation. The magnetic field is not separate from Earth. It begins with motion inside the liquid outer core. The dynamo idea connects moving conductive metal below with magnetic behavior surrounding the entire planet above. A compass needle on a table quietly responds to a field wrapped around the whole Earth. That simple movement raises a larger question: how does an invisible field become visible in the sky? Unlike the unreachable core, spacecraft can fire through Earth's magnetic environment and sample its changing conditions. Charged particles do not always travel straight. Magnetic fields can bend their paths into readable curves. The story of the liquid core now rises outward from hidden metal to the sky above. How can motion deep inside Earth help create lights that shimmer near the planet's poles at night? Under polar darkness, auroras reveal the magnetic story in colors the human eye can follow upward. A person standing beneath those lights is connected to the core, the atmosphere, and the sun. Some charged particles are guided toward polar regions, where the upper atmosphere can begin to glow. Auroras are not decorations in the sky. They are visible clues of a planet-space interaction above us. When energized particles strike upper atmosphere gases, atoms release light in shifting curtains and colored arcs above Earth. But the glowing sky raises another question: how steady is the shield shaping this display over time? The magnetosphere is not frozen around Earth. Solar wind can stretch and compress its shape continuously. On Earth's night side, the magnetic environment trails backward like a long wake in space behind us. It is better understood as a dynamic region, not a rigid shell surrounding the planet forever. Satellites detect changing particles and magnetic conditions, turning invisible space weather into measurable scientific evidence for researchers. Even when the field works, strong space weather can still disturb technology above the surface today. Satellites, communications, and navigation systems all operate inside conditions partly shaped by Earth's magnetic field. Every day, small human machines move through a vast planetary environment linked to motion far below them inside Earth. Solar wind, pressure's magnetic field push against each other continuously, reshaping the boundary in space. Charged particles curve along invisible paths, revealing structure where empty space seems almost featureless to us. To make that invisible structure familiar, the investigation returns to one small instrument, a simple compass. A compass brings the planet's magnetic field down to human scale, resting quietly in a hand, long before satellites' magnetic direction helped travelers cross oceans, forests, deserts, and unfamiliar coastlines safely at night. Today, observatories track slow magnetic changes with instruments far more sensitive than any pocket compass can be. A small shift in local direction belongs to a changing field spanning the entire planet around us. In quiet instrument rooms, tiny needle movements become data about a restless magnetic system beneath and above. A compass needle aligns with the local direction of Earth's magnetic field, not with magic or guesswork. Magnetic north and geographic north are different points, and that difference changes slowly over time on maps. Scientists compare ground stations and satellites to watch magnetic changes from below and above the atmosphere. Modern life depends on systems working inside this space environment, from satellites to navigation signals every day. The field feels steady during daily life, yet its deeper behavior is always changing beneath appearances. When solar activity intensifies, magnetic conditions around Earth can become more disturbed and unpredictable for technology. Those disturbances can energize polar skies, making auroras brighter, wider, and sometimes visible farther south than usual. Instruments record these events as measurable disturbances, not just beautiful lights in the night sky above us. Magnetic disturbances move through the environment unevenly, reaching some regions before others begin to respond later. A local aurora can be the visible edge of a planet-scale magnetic structure overhead at night. For scientists and sky watchers, the same event becomes both evidence and wonder at once together. Earth's magnetic field is not a permanent frozen shape. It shifts under changing forces around us. Core motion, magnetic fields, solar particles, and glowing air form one connected planetary system together above us. So the investigation returns downward toward a hidden source controlling this invisible shield from below Earth. The sky has shown the field's effects, but the engine still waits deep inside Earth below. That faint arc from the core now widens, wrapping Earth in a magnetic environment, reaching far beyond rock. From space, the shield grows larger than the planet itself, stretching into a vast invisible neighborhood. Solar wind does not hit Earth like rain on glass. It bends, streams, and reshapes the field. The magnetosphere is squeezed toward the sun, while its long tail trails behind Earth into darkness. In control rooms and satellites, scientists watch those disturbances because modern systems depend on magnetic conditions. A changing line on a monitor can reveal motion thousands of miles below the familiar surface. Near the poles, invisible magnetic interactions sometimes become visible as curtains of moving green and violet light. An aurora begins with the sun, but its pathway is guided by Earth's hidden magnetic engine. Charged particles follow magnetic geometry, funneling toward polar skies instead of spreading evenly across the planet. The glowing sky becomes a clue, pointing from space weather back toward the liquid metal below. A simple compass on a kitchen table quietly responds to a field surrounding the entire planet. The needle is not being pulled by a place called north, but aligning with Earth's magnetic field. That small movement connects a backyard instrument to patterns that stretch across oceans, continents, and near Earth space. Magnetic observatories track slow changes, turning invisible field behavior into records scientists can compare over decades. The field is not frozen in place, because the core beneath it is not frozen either. Pilots, satellites, and navigation systems all depend on updates when Earth's magnetic map slowly shifts. Human technology adapts because the planet's magnetic direction is useful, but never perfectly permanent or perfectly simple. Some of the strongest records are not digital, but hidden inside old volcanic rocks and seafloor crust. As lava cools, tiny magnetic minerals can lock themselves toward the field direction of that moment. Those ancient directions show the field has changed before, leaving a deeper question beneath every measurement. Earth's magnetic poles wander over time, making the planet feel less like a fixed machine. That movement is normal field behavior, not proof that disaster is waiting around the nearest corner. A volcanic stone can become a memory chip, preserving magnetic direction long after the lava hardens. Magnetic reversals are real, but they unfold across geological time, not like a sudden movie switch. On the surface, life can seem ordinary, while deep magnetic patterns slowly reorganize far below us. To understand those changes, the journey must leave the glowing sky and descend toward the core again. The liquid outer core supplies the moving conductor, where rotation and convection keep the dynamo alive. Inside that metallic ocean sits another world, solid, compressed and surrounded by restless, flowing metal currents. But how can anything remain solid here, where temperatures may rival the surface of the sun? At Earth's center, heat alone cannot explain the strange solid world buried inside the planet. The inner core is not a hollow chamber, but a vast metallic sphere under crushing pressure. That pressure changes the rules, forcing matter into structures that surface conditions could never sustain naturally. Heat pushes iron toward melting, but pressure can hold atoms tightly enough to remain solid inside. So the deepest surprise is not simply temperature, but the balance between heat and crushing pressure. Scientists infer this solid center by watching how seismic waves bend, slow, and pass through Earth. Different waves behave differently underground, giving researchers a kind of shadow map of the planet's interior. Their speed and direction clues about density, structure, and possible patterns inside the inner core. No camera reaches this place, so the evidence comes from repeated measurements and careful, scientific comparison. The inner core is known well enough to matter, yet mysterious enough to keep changing questions. Now, the investigation shifts from what the inner core is to what it may be doing. At its boundary, solid metal meets liquid metal, creating one of Earth's most important contact zones. As the inner core slowly grows, it may release heat and lighter material into the outer core. That release can help stir the surrounding liquid metal, adding energy to the core's moving system. Heat and chemistry work together, shaping the long-term engine that supports Earth's magnetic field above. The solid center may influence the liquid around it, meaning apparent stillness can help drive motion. Scientists compress tiny samples to test ideas about conditions no machine can ever visit. A sample smaller than a coin can help explore pressures greater than anything at the surface. Even so, the inner core remains partly uncertain, with models improving as new evidence slowly arrives. Surface instruments are still our doorway, translating distant vibrations into clues about the deepest central world. What could the inner core's structure reveal about Earth's past, its engine, and its future? At the inner core boundary, the molten glow fades into something strangely rigid, compressed, and almost crystalline. Extreme pressure changes the rules, forcing iron, rich material, to stay solid despite unimaginable heat near the center. It is like placing impossible weight on 1 square inch until atoms have little room to move. In laboratories, tiny samples are squeezed between diamonds, giving scientists clues about deep core conditions on Earth. Heat matters, but pressure decides whether this hidden metal can flow freely or remain locked in place. No drill has reached this world. Every image here is built from instruments, experiments, and careful models. Seismic waves act like messengers, changing speed and direction as they pass through different hidden layers inside. Some waves suggest the inner core may carry structure, with signals traveling differently depending on direction. The evidence is strong, yet the inner core still keeps some of its behavior unresolved by science. To understand that mystery, the investigation turns toward the signals that cross Earth after earthquakes worldwide. A quiet mountain or coastline can hold the first trace of movement from far below today. Sensitive instruments record tremors too small to feel, converting Earth's hidden motion into visible lines for scientists. Waves travel one way through solid metal and another through liquid layers surrounding it below Earth. Why do some earthquake waves disappear from certain places, leaving shadow zones across the globe below? A tiny motion at the surface can reveal the shape of structures thousands of miles deep. Scientists compare records from many stations, turning scattered signals into a rough map of Earth's interior, from deserts to cities. Every monitoring station becomes one listening post for the planet's center below. When waves slow, bend, or brighten, they hint at density, temperature, and hidden structure inside Earth. Even with global measurements, the deepest center remains partly known through echoes rather than sight itself. Now the question shifts from what the core is to how it changes over time slowly. Was the inner core always solid, or did it grow slowly as Earth lost heat below? As the planet cools, iron can crystallize at the boundary, adding material to the inner core. Each small crystal connects to a planetary engine, moving heat and energy across enormous distances underground. These patterns are scientific visualizations, not photographs, showing one-way iron may organize under pressure below. Laboratory data and seismic waves narrow the possibilities, but they do not close the case completely. The deepest solid sphere is not just a remnant, it may be evidence of Earth cooling. That slow cooling links the core to the planet's age, chemistry, and long-term evolution over time. Scientists still debate when the inner core formed and whether its behavior changes over time inside. Better instruments can revise the story because deep Earth science grows through indirect evidence and testing. The camera now leaves the solid center, following energy outward toward moving liquid metal again above. As iron freezes, it can release heat and lighter elements into the surrounding outer core fluid. That released energy helps drive motion, keeping the liquid metal from settling into stillness below Earth. The inner core is not separate from the engine. It may help keep that engine alive. At the surface, the first clue is simple: a compass direction is not truly fixed forever. The needle trembles slightly, showing that Earth's magnetic field is always changing beneath familiar skies above. Magnetic north moves over time, drifting across maps rather than staying nailed to one point forever. A small compass shift connects your hand to a magnetic system wrapped around the whole planet. Field lines change because the liquid outer core keeps moving, twisting, and reorganizing below Earth today. If the field can wander, what else can change in Earth's invisible shield over time ahead? The investigation now leaves modern instruments and enters rocks that remembered the field long before humans. When lava cools, it can preserve a magnetic snapshot from the moment it became solid rock. Tiny magnetic minerals turn like microscopic compass needles before the cooling rock locks them in place. Once the rock hardens, that direction becomes a record, waiting millions of years to be read. Researchers sample ancient flows, carrying pieces of Earth's magnetic memory back to the lab for testing. One small rock contoured a vast timeline of planetary change and deep motion below. On the ocean floor, magnetic stripes reveal that the field has reversed again and again before. The compass direction we trust today has flipped many times during Earth's deep history before humans. These reversals are real geological processes, not instant disasters sweeping across the surface in minutes globally. The rock record proves change, but it does not make the next reversal easy to predict. Next, the story asks why magnetic reversals happen and why they are so often misunderstood today. Magnetic north is not standing still. It drifts across Arctic maps, revealing a field still alive beneath us. A handheld compass turns the planetary movement into one small trembling needle, something anyone can watch in silence. That tiny needle points to a structure wrapping the whole planet, far larger than any map can show. Observatories measure the field year after year, catching changes too small for ordinary senses to notice. Those careful surface readings becomes about liquid metal motion thousands of miles beneath the crust. Maps make the poles look fixed, but Earth has never promised its magnetic landmarks would stay put. When volcanic rock cools, tiny minerals can freeze a snapshot of the magnetic field around them. As lava hardens, magnetic grains align lock, turning ordinary stone into an ancient directional record. If rocks can remember old fields, they can also reveal times when Earth's magnetism changed direction. So why does the seafloor contain stripe patterns that look almost like a planetary magnetic barcode? Across mid-ocean ridges, bands of magnetized rock appear in matching patterns on both sides of the ridge. New crust forms, cools the magnetic direction that existed at that exact geological moment. Those mirrored stripes became powerful evidence that Earth's magnetic field has reversed many times in the past. A small rock sample can carry a signal from a magnetic world millions of years gone. Researchers never see that ancient field directly. They reconstruct it from measurements, minerals, and careful comparisons. A reversal means magnetic north and south trade roles, but across geological time, not sudden minutes. The idea sounds dramatic, yet reversals do not unfold like someone flipping a planetary switch overnight. Their timing stretches far beyond a human life. Across intervals only rocks can patiently record for us. Disaster stories often compress reversals into instant chaos, but the evidence points to much slower change. Still, a wandering field raises a deeper question. What is happening inside the engine that makes it? To answer that, the investigation must leave the rocks and descend again beneath the mantle's lower boundary. Inside the outer core, liquid metal flows in twisting paths, never as one simple underground river. Small changes in those flows can ripple into patterns large enough to affect the whole planet. Earth's rotation helps organize some motion into columns, linking deep metal currents to a spinning world. The dynamo is not a machine with gears, but a process driven by moving, conductive fluid. When that flow reorganizes, the magnetic field can weaken, wander, or build itself differently over time. Today, satellites watch these changes from orbit, mapping the field across nearly the entire planet in detail. Some regions show weaker magnetic strength, giving scientists important places to monitor more closely over time. A weak region does not prove collapse. It is one clue inside a larger, changing system. How much can Earth's magnetic field change before technology, satellites, or power grids begin to notice? If the shield weakened, more charged particles could reach the region where satellites and spacecraft operate. That makes power systems, navigation networks, and orbital hardware part of the practical scientific concern for engineers. For people on the ground, space weather becomes less abstract when technology begins responding to it. The same solar particles that create auroras can also expose weaknesses in our modern technological infrastructure. Past reversals show magnetic change is part of Earth's history, not a violation of the planet's rules. Life and geology continued through many magnetic changes, though the details remain complex, uneven, and debated. But changing magnetism is not the same question as what happens if the engine itself slowly fades. If Earth's core went quiet, would the first signs appear in the sky, ground, or time itself? This chapter is a hypothetical investigation, not a prediction that something sudden is beginning now on Earth. To imagine a quieter core, scientists often compare Earth with planets that followed very different paths. Mars still carries traces of an ancient magnetic field, preserved mostly in scattered patches of crust. Those remnants suggest Mars once had a more active interior magnetic story than it does today. A planet can begin with stronger protection and still lose much of it over deep time. Without a strong global field, an upper atmosphere meets space weather more directly and more persistently. Earth is not Mars, but Mars helps reveal why internal engines matter to long planetary futures. Earth's core changes slowly because heat escapes outward through layers over immense stretches of geological time. A quieting core would be a deep time transformation, not a sudden movie style disaster sequence tomorrow morning. Technology would likely notice magnetic weakening long before ordinary streets, forests, or coastlines look noticeably different. From a backyard, Earth could seem unchanged while hidden systems beneath and above us slowly shifted. The real mystery is not whether the core matters, but how long its engine can endure. This is not a prediction for tomorrow, but a thought experiment about Earth's engine over deep time. If the core changed, its effects would move slowly through layers, atmosphere, space over time. A quieter dynamo would begin with weaker motion inside electrically conducting liquid metal far below us. A tiny shift at Earth's center could eventually spread into a planet-sized magnetic change around us. Satellites would likely notice the first subtle field changes long before people felt anything at ground level. Auroras show we're charged part of Earth's magnetic environment, turning invisible physics into colored light above us. With a weaker field, space weather could interact more strongly with the region around our planet. Satellites, navigation systems, and power networks would be realistic places to watch for possible effects first. A neighborhood could look completely normal, while invisible systems above and below it slowly shift together. To understand that possibility, scientists often compare Earth with a colder, quieter world next door, Mars. A dry desert can suggest Mars, but comparison does not mean Earth would follow the same path. Mars matters because it no longer has a global magnetic field like the one surrounding Earth today. Some Martian rocks still carry ancient magnetic signatures, like frozen memories of an earlier planetary engine. That fossil magnetism hints at past activity, not a living global shield operating across Mars today. Local magnetic traces can survive long after a planet's larger dynamo has weakened or disappeared completely. Mars is a warning and a clue, but not a simple map of Earth's future story. Atmosphere, gravity, solar wind, and magnetism all shape how space weather touches a planet's surface environment. Losing atmosphere is complicated, so the magnetic field is only one piece of a much larger system. Researchers compare planets using spacecraft, lab measurements, and models, because certainty is rarely handed to them. So why has Earth's hidden engine, running while other planetary dynamos changed or faded away? The answer belongs to deep time, where millions of years pass like slow internal weather patterns. Heat escaping from the core helps drive larger interior processes that reshape Earth over geologic time. Volcanoes are not windows into the core, but they reveal that Earth's interior remains active below. The mantle and the core are connected, yet they are not the same physical system inside Earth. At the surface, rocks can preserve clues about magnetic behavior that happened long before humans existed. Across the ocean floor, magnetic patterns record repeated changes in Earth's field through ancient crustal rock. When lava cools, minerals can lock in the direction of the magnetic field at that time. A compass feels simple because it hides a restless history written into stone and seafloor patterns. The dynamo can change strength and direction, but its exact future remains difficult to forecast clearly. From planetary timescales, the story now returns to the instruments, trying to read them carefully. Core science is built from indirect evidence, careful models, and comparisons that can be tested repeatedly. Observed signals are one thing, the explanations built from them must stay honest and cautious always. Seismic waves remain among the clearest messages sent from regions no machine can reach today directly. A small seismometer can reveal structures lying thousands of miles beneath a quiet surface above us. Iron-rich meteorites offer clues about planetary materials, even though they are not pieces of Earth's core. Laboratory experiments recreate fragments of deep conditions, but never the entire pressure, heat, and scale together. A tiny metal sample can still help investigate the largest hidden system inside our planet today. The uncertainty matters because ordinary life depends on planetary machinery most people never notice directly beneath them. Auroras remind us that deep Earth and distant space are connected through invisible magnetic architecture overhead. Now the question narrows again. What answer best fits the clues we actually have today scientifically? Earth's core links internal heat, magnetic behavior, and the long future of the planet itself together. Above it all, people drive, sleep, and watch weather under forces they cannot see directly below. The best answer combines seismic waves, magnetic measurements, lab experiments, and planetary models into one picture. Each tool reveals one part of the core, while leaving another part in shadow below Earth. The core is unseen, yet few hidden places on Earth leave so many measurable clues behind. The inner core remains mysterious because pressure, heat, and composition reach conditions beyond direct human experience. The hypothetical ends here, but the deeper question remains beneath every familiar surface we know today. So we return from possibility to evidence, and to the strongest answer science currently supports today. Seismic waves show a liquid outer core surrounding a smaller, solid inner core deep below us. Together, those layers form the moving metallic engine behind much of Earth's magnetic behavior today above. After the imagined future fades, we return to the present, where evidence is quieter, but far stronger. Scientists know the core through signals, models, and measurements, not through cameras lowered into the planet. Each major earthquake sends waves through Earth, turning the whole planet into a vast scientific instrument. Where those waves bend, slow or vanish, they reveal boundaries hidden far beneath any possible drill. The strongest picture suggests moving liquid metal, carrying heat and electrical energy through the outer core. From that buried motion, a planet-sized magnetic field can rise far beyond the surface we know. That field reaches into near-Earth space, where solar particles meet an invisible boundary around our world. Sometimes the hidden engine announces itself in color, as auroras shimmer above dark polar skies at night. A quiet neighborhood may feel separate from deep Earth, yet it rests on that same system. The ground beneath a city block is only a thin outer skin over a layered planet. Crust, mantle, core, atmosphere, and are not separate stories, but parts of one connected machine. Science can be confident and humble at once, especially when the destination remains impossible to reach. Seismic waves, gravity, magnetism, and laboratory experiments all point toward the same hidden interior structure below us. The best answer is layered and metallic, a liquid outer core surrounding a solid inner center. Yet important questions remain about flow, patterns, heat loss, and how the inner core changes over time. The paradox, simple Earth center, is one of our best known places we cannot visit. Every new measurement sharpens the picture, but also reveals details that earlier models could not show. Instruments at the surface listen for tiny clues from a world thousands of miles below our feet. Small tremors become global maps, turning faint motion into evidence for an unseen interior far below. This is the hidden engine, not a metaphor for fantasy, but for connected planetary motion below us. Its influence may reach from molten metal to magnetic shelter, from deep pressure to living landscapes. A compass needle on a kitchen table points toward a process larger than any continent on Earth. That tiny movement links your hand to currents moving in darkness near Earth's center below everything. The surface feels familiar because we live here, but familiarity can hide the deepest mystery beneath us. What would Earth look like if we could see the engine directly, even for 1 second? For now, the answer comes through evidence, not sight, and that makes the mystery even stronger. Earth's core is not one fact, but a system of heat, metal, motion, and time. Once you understand that, ordinary ground no longer feels ordinary. It becomes the roof of another world. Above us, Earth is home. Beneath us, it remains a planet still being discovered every day. And at its center, the unseen engine keeps turning beneath every ocean, forest, highway, and home.